Welcome, everyone. I'm excited to kick off today's presentation on probability. This is the first slide, so I just want to warmly welcome you all and introduce the topic. The title is simply Probability, and it sets the stage for what we'll be exploring together. We'll cover key concepts, applications, and how probability impacts various fields. So let's get started and dive into the fascinating world of probability. Now, moving on to slide 2, we see that this section covers some advanced examples in probability. First, we'll discuss the properties of probability, which are fundamental to understanding how probabilities behave in different scenarios. Then, we'll look at some specific examples to see these properties in action. Next, we'll explore the various types of probability, helping us understand the different ways probability can be categorized. After that, we'll examine an interesting case, tossing 3 coins, to see how probabilities work with multiple events happening simultaneously. This slide also marks the completion of our chapter on probability, highlighting the key terms we've learned so far. Finally, we'll touch on some practical applications of probability in real life, showing how these concepts are useful beyond the classroom. Throughout this section, keep in mind that understanding these advanced examples will deepen your grasp of probability and its real-world relevance. Welcome to our introduction to probability. Today, I want to start by explaining what probability really is. At its core, probability is a way to measure how likely an event is to happen. It's a fundamental concept that helps us understand and quantify uncertainty in everyday life and in many fields like science, economics, and engineering. We'll explore how probability gives us a structured way to predict outcomes when there's some element of randomness involved. Think of flipping a coin or rolling dice. These are simple examples where probability helps us grasp the chances of getting heads or a specific number. As we go along, keep in mind that probability isn't just about guessing. It's about using data and logic to make informed predictions. This understanding sets the foundation for everything else we'll cover in this course, from statistical analysis to decision-making under uncertainty. So, let's dive in and see how probability shapes the way we interpret the world around us. Today, we're diving into a fascinating area of mathematics, one that helps us understand uncertainty. This branch specifically measures how likely or unlikely events are to happen, and that's what we call probability. When we talk about probability, we're essentially trying to quantify the chance that a specific outcome will occur. It's a way of putting a number on uncertainty, making it easier to analyze and make decisions based on what might happen next. As we explore this concept, keep in mind that probability is fundamental not only in math, but also in everyday life, from predicting weather to making strategic choices. So, understanding probability gives us a powerful tool to interpret the world around us more confidently. Now, let's talk about the words we use to describe the likelihood of an event happening. We often say things like impossible, unlikely, possible, even chance, likely, and certain. These words help us communicate how probable something is. For example, I might say, "It is unlikely to rain tomorrow," which means the chance of rain is low but not 0. In terms of probability as a number, it ranges from 0 to 1. 0 means impossible, something that cannot happen at all. 1 means certain, something that will definitely happen. The numbers in between represent different degrees of likelihood. So the key idea here is that probability is all about quantifying the chance that something will occur. When we talk about possible outcomes, we're really talking about all the different things that can happen in a given situation, each with its own probability. Understanding this helps us make better predictions and decisions based on how likely different outcomes are. Let's take a closer look at some key terms in probability that are essential for understanding the concepts we'll be exploring today. First, the idea of a probability itself is a measure of how likely an event is to happen, ranging from 0, meaning it can't happen, to 1, meaning it's certain to happen. This helps us quantify uncertainty in a clear way. Next, we have sample space, which is simply all the possible outcomes of a situation. For example, if you're rolling a die, the sample space includes all the numbers from 1 to 6. Understanding the sample space is crucial because it forms the foundation for calculating probabilities. Then we encounter event, which is any specific outcome or set of outcomes within the sample space. For instance, rolling an even number is an event. Another important term is probability model, which is a mathematical framework that describes how probabilities are assigned to different outcomes. This model helps us make predictions and analyze random processes more systematically. Finally, understanding independent and dependent events is vital. Independent events are those where the outcome of one doesn't influence the other, like flipping a coin and rolling a die. Dependent events, on the other hand, are affected by previous outcomes, like drawing cards without replacement. By grasping these key terms, we build a solid foundation for analyzing and interpreting probability, which ties directly into our overall goal of understanding how randomness and uncertainty work in various scenarios. A trial is when the experiment is performed once. It's what we call an empirical probability because it's based on actual data from that single run. Think of it as a real-world test, like flipping a coin one time and seeing if it lands on heads or tails. Each of these individual runs or attempts is what we refer to as a trial. Understanding trials is fundamental because they provide the raw data we need to analyze and estimate probabilities in real situations. So, whenever we talk about the likelihood of an event happening, we're often referring to the results of these trials. This connection helps us see how probability works in practice, not just in theory. An outcome is essentially a result of a random experiment. For example, if we think about rolling a die, the specific number that comes up, say, a 6, is what we call an outcome. The key point here is that outcomes are the possible results that can happen when we perform a random experiment. And understanding outcomes helps us analyze probabilities because it defines what we're actually measuring or predicting. So, in the context of probability, focusing on outcomes allows us to clearly identify what we're looking at when we consider different possible results and their likelihoods. Now, let's take a closer look at what an event really is. An event in probability can have just a single outcome, or it can include multiple outcomes. Think of it this way. An event is essentially a set of outcomes. For example, if we roll a die and we're interested in the event of getting a number less than 5, that set includes the outcomes 1, 2, 3, and 4. So in this case, the event is rolling a number less than 5, and it includes all those outcomes. It's important to remember that when we're talking about an event, we're really talking about a collection of outcomes that share some common characteristic. And understanding this helps us analyze probabilities more effectively. This concept ties into the overall theme of probability because it shows us how we can group outcomes to evaluate the likelihood of certain events happening. Whether it's a single outcome or multiple, framing events this way allows us to calculate and interpret probabilities in a clear, structured manner. Let's take a closer look at this example. When we talk about a single trial of an experiment, such as flipping a coin, there are only two possible outcomes, heads or tails. So, for just one toss, the outcome is limited to either head or tail. Now, in probability, when an event has only one specific outcome out of all possible outcomes, we call that an elementary event. It's like focusing on a single, unique result within the entire experiment. Recognizing elementary events helps us understand the basic building blocks of probability and how individual outcomes contribute to the bigger picture. This concept is fundamental because it allows us to analyze and predict the likelihood of specific results in any random experiment. An event that has no chance of occurring is called an impossible event. So, in terms of probability, we write this as P, E equals 0. This means that the likelihood of this event happening is 0, essentially impossible. For example, imagine trying to roll a 7 on a standard 6-sided die. It's simply not possible because the die doesn't have a 7. Recognizing impossible events helps us understand the boundaries of what can happen in any experiment or trial. It's a fundamental concept because it sets the baseline for understanding probabilities, showing us what's out of the realm of possibility. Throughout our study of probability, keeping in mind these impossible events helps us build a clearer picture of what outcomes are feasible and which are not. Let's talk about the concept of a sure event. When we say that the probability of an event is 1, it means that this event is certain to happen. For example, imagine rolling a die. The probability that you get a number less than 7 is actually 6 out of 6, which simplifies to 1. This illustrates that some events are guaranteed to happen. In probability, when an event has a 100% chance of occurring, we call it a sure event. It's the kind of event that we can be absolutely certain about, no matter what. Understanding sure events helps us grasp the fundamentals of probability because they serve as the benchmark for certainty within the range of all possible outcomes. So, in summary, a sure event is one that will definitely happen, and its probability is always equal to 1. Let's take a closer look at the different types of probability. When we talk about probability, we're essentially discussing the likelihood of an event happening. There are a few key types to understand. First, there's theoretical probability, which is based on the assumption that all outcomes are equally likely. For example, flipping a fair coin has a theoretical probability of 50% for heads or tails. Next, we have experimental probability, which is determined through actual experiments or trials. So, if you flip a coin 100 times and get 55 heads, the experimental probability of heads is 55%. Lastly, there's subjective probability, which is based on personal judgment or experience rather than strict calculations. This is often used in real-life situations where data might be limited or uncertain. Recognizing these types helps us better understand and apply probability in different contexts, connecting to the overall theme of making informed decisions based on likelihood. Experimental probability can be applied to any event that is part of an experiment, especially when that experiment is repeated many times. The idea is that by performing a large number of trials, we can get a better estimate of the likelihood of an event occurring. This approach is really useful because it relies on actual data from experiments rather than just theoretical calculations. As we've seen earlier, probability can be both theoretical and experimental probability gives us practical insights. Remember, the more times we repeat the experiment, the more accurate our estimate becomes. This concept ties into the overall theme of understanding how probability works in real-world situations, helping us make predictions based on observed outcomes. Let's take a closer look at this formula. P(E) equals the number of trials where the event occurred divided by the total number of trials. This represents what's called experimental or empirical probability. Essentially, it's a way to estimate the likelihood of an event based on actual data or observations. Instead of relying on theoretical assumptions, we're looking at real-world results. The key idea here is that by conducting experiments or trials and recording the outcomes, we can calculate the probability of an event happening. This approach is especially useful when theoretical probability is difficult to determine. Remember, the more trials we perform, the more accurate our estimate tends to be. So, this formula connects directly to the overall theme of understanding and predicting outcomes through data. Let's take a closer look at this formula for probability. P of E, which stands for the probability of event E happening, is equal to the number of outcomes that are favorable to E divided by the total number of possible outcomes in the experiment. Essentially, this means we're looking at all the ways event E can occur and comparing that to all the possible outcomes that could happen in the experiment. Now, when we talk about theoretical probability, we're referring to this kind of calculation, based on what should happen in an ideal, perfectly random situation. It's a way to predict the likelihood of an event occurring before any actual experiment is done, based purely on the possible outcomes. This concept is really important because it helps us understand the expected chances of an event, which is fundamental in making predictions and decisions in probability. And as we go through the presentation, keep in mind how this formula ties into the broader ideas of predicting and analyzing outcomes in various scenarios. Let's take a closer look at the properties of probability. First, it's important to understand that probability values always range between 0 and 1. A probability of 0 means an event is impossible, while a probability of 1 indicates certainty that the event will happen. Next, consider how probabilities behave in relation to different events. For mutually exclusive events, those that cannot happen at the same time, the probability that either one occurs is simply the sum of their individual probabilities. This is called the addition rule. On the other hand, when we're dealing with independent events, events where the outcome of one doesn't influence the outcome of another, the probability that both occur is found by multiplying their individual probabilities. This is known as the multiplication rule. Understanding these properties helps us accurately assess the likelihood of various scenarios, which is central to the overall theme of probability. It allows us to model real-world situations more effectively and make informed decisions based on these probabilities. Now, let's look at the concept of the complement of an event. The event E, which stands for not E, is called the complement of E essentially. It includes all the outcomes where E does not happen. An important point here is that the probability of E plus the probability of its complement, E, always equals 1. This makes sense because either E occurs or it doesn't. Those are the only two possibilities, so their probabilities together must cover the entire sample space. Next, let's talk about the range of probabilities for any event. Probabilities are always between 0 and 1, inclusive. That means the probability of an event can be 0, indicating it's impossible, or 1, meaning it's certain to happen. All other probabilities fall somewhere in between. To clarify this, consider a simple example like tossing a coin. The probability of getting heads is 1/2, and the probability of getting tails is also 1/2. When you add these together, you get 1, which confirms that the total probability across all possible outcomes in the experiment sums to 1. This is a fundamental principle in probability theory. The sum of the probabilities of all elementary events in an experiment must always be 1. So, in summary, the idea of complementary events helps us understand the relationship between an event and what it excludes, and knowing that probabilities are bounded between 0 and 1 ensures our calculations stay realistic within the framework of probability. And finally, the total probability across all possible elementary outcomes in any experiment always sums to 1, which keeps our probability models consistent and complete. Now, let's explore some real-life applications of probability. As we've seen throughout this presentation, probability isn't just a theoretical concept. It's something that influences many aspects of our daily lives. For example, in weather forecasting, we use probability to predict the chances of rain or snow, helping us plan our days better. In healthcare, probability models help doctors assess the likelihood of diseases and determine the best treatment options. Similarly, in finance, investors use probability to evaluate risks and make informed decisions about investments. Even in sports, coaches and analysts use probability to strategize and improve team performance. These examples show how understanding probability can help us make smarter choices and better understand the world around us. It's a powerful tool that bridges the gap between theory and everyday decision-making, reinforcing the importance of what we've learned today. Let's take a moment to consider voting, one of the most common applications of probability in our daily lives. When we vote, we're often making decisions based on uncertain outcomes, and probability helps us understand and interpret those risks. For example, predicting election results involves analyzing polling data and estimating the likelihood of different outcomes. This use of probability helps in making more informed decisions, whether you're a campaign strategist or a voter. Voting also highlights the importance of understanding probabilities when assessing trustworthiness and credibility. If a poll shows a candidate leading by a small margin, probability can help us gauge how confident we should be in that result. It's a great example of how probability isn't just theoretical. It's a practical tool that influences real-world decisions we make every day. So, in the context of our overall theme, voting illustrates how probability helps us navigate uncertainty, make predictions, and ultimately, make better choices in situations that impact society as a whole. Let's talk about flipping a coin. This might seem like a simple act, but it actually illustrates some very important concepts in probability and randomness. When you flip a coin, there are two possible outcomes, heads or tails. Each outcome is equally likely, assuming the coin is fair. This symmetry is what makes coin flips a great example of a random experiment. Now, the key point here is that each flip is independent. That means the result of one flip doesn't influence the next. Whether you get heads or tails this time, the odds are still 50-50 for the next flip. This idea of independence is crucial when we're analyzing random processes. It helps us understand how probabilities behave over multiple trials. Overall, flipping a coin is a simple but powerful way to grasp the fundamentals of probability, randomness, and independence, core themes that run throughout this entire presentation. When we toss a coin, there are only two possible outcomes, heads or tails. It's a classic example of a simple probability situation. Each outcome, heads or tails, is equally likely, which makes it a perfect way to introduce the concept of randomness. This basic idea helps us understand how we can model and predict the likelihood of different events. Remember, even though the outcome seems random, the probability of each side showing up is always 50% when the coin is fair. This concept of two outcomes is fundamental in probability theory and connects to many other real-world scenarios where there are only two possible results. Today, we're going to explore what happens when we toss two coins. This simple action actually introduces us to some fundamental concepts in probability. When you flip two coins, there are four possible outcomes. Both coins land heads, both land tails, or one heads and one tails. Understanding these outcomes helps us see how probabilities are distributed in a random process. It's a great way to visualize how chance works in everyday situations. By examining these results, we can better grasp the principles of probability that underpin many other areas, from games to decision-making. So, let's think about how each of these outcomes contributes to the overall likelihood of different events happening. Let's consider what happens when we toss three coins. This might seem simple, but it actually introduces us to some fundamental concepts in probability. When we flip three coins, each coin has two possible outcomes, heads or tails. The key point here is that the total number of possible outcomes increases as we add more coins. Specifically, with three coins, there are 8 possible outcomes like HHH, HHT, HTH, HTT, THH, THT, TTH, and TTT. This example helps us understand how probabilities are distributed across different outcomes. It also highlights the importance of understanding all possible outcomes when calculating probabilities in more complex situations. As we move through the presentation, keep in mind that this simple experiment of tossing coins is a great way to grasp the basics of probability theory and how it applies to real-world decision-making. Let's consider the simple act of tossing three coins. This might seem straightforward, but it's actually a great way to explore probability and randomness. When we flip three coins, each coin has two possible outcomes, heads or tails. The key point here is that the combined outcomes can vary quite a bit, from all three showing heads to all three showing tails, or any combination in between. By examining these possible outcomes, we can understand how probabilities distribute across different scenarios. It highlights how some results are more likely than others, depending on the combination. This example ties into our overall theme of understanding chance and decision-making under uncertainty. Tossing three coins is a simple model, but it helps us grasp fundamental concepts in probability theory that are essential for more complex decision processes. So, as we move forward, keep in mind how such basic experiments underpin much of what we analyze in data and risk assessment. Let's take a moment to focus on coins. Coins are a fundamental part of our financial systems and everyday transactions. They represent the tangible, physical aspect of currency that people have used for centuries. When we talk about coins, we're really highlighting their role in facilitating trade and exchange, especially in small-value transactions. Coins are also interesting because they often carry cultural and historical significance through their designs and inscriptions. They can tell us a lot about a country's history, values, and leadership at a given time. In the context of our overall theme, coins remind us of the importance of tangible assets and the evolution of money. While digital currencies are on the rise, coins still hold a crucial place, especially for small transactions and for understanding the roots of our monetary system. So, as we move forward, keep in mind how coins symbolize both tradition and the enduring nature of currency in our economic lives. All right, so here we see that the total number of outcomes when rolling a die is 6. That's because the outcomes are simply the numbers 1 through 6. We can think of the outcomes as the possible results you can get from a single roll, which are represented here as the set 1, 2, 3, 4, 5, 6. When you roll a die, each of these outcomes is equally likely, assuming it's a fair die. This concept is fundamental because it helps us understand probability. Knowing all the possible outcomes is the first step in calculating the chance of any particular result. And, of course, this ties into the overall theme of understanding randomness and probability in everyday situations. Let's look at some examples to bring these ideas to life. These examples will help clarify the key points we've discussed so far. You'll notice how they illustrate the concepts in a practical way. Highlighting these real-world cases makes the information more relatable and easier to understand. Connecting these examples back to our overall theme reinforces the importance of applying these principles effectively. Remember, the goal is to see how theory translates into practice, ensuring you're prepared to implement these ideas confidently. Let's look at some common examples of experiments and their outcomes. First, imagine a driver trying to start a car. The outcome is either the car starts or it doesn't. Next, think about a player shooting a basketball. She or he either makes the shot or misses. Then, consider a trial where someone answers a true-false question. Either the answer is right or wrong. Finally, picture a baby being born. It's either a boy or a girl. Now, the key question here is, which of these experiments have outcomes that are equally likely? In other words, in which cases do both outcomes have the same chance of happening? This is important because understanding the likelihood of different outcomes helps us analyze probabilities better. For instance, the outcomes of a car starting or not starting might not be equally likely, depending on conditions, whereas the birth of a boy or a girl is generally considered equally likely. By examining these examples, we can see that some experiments, like the birth of a baby, are naturally symmetric, meaning both outcomes are equally probable. Others, like starting a car, might not be, especially under certain conditions. So, in your analysis, think about the inherent probabilities in each scenario and whether the outcomes are symmetric or not. This understanding is fundamental for the overall theme of probability and how we evaluate uncertainty in different situations. Let's start with the first point. The probability of an event E plus the probability of the event, not E, equals. This highlights a fundamental concept in probability, that these two probabilities together always cover all possible outcomes of an experiment. Essentially, either an event happens or it doesn't, and their probabilities sum to 1. Moving to the second point, the probability of an event that cannot happen is, this probability is 0. We call such an event impossible because it has no chance of occurring. It's important to recognize these impossible events as a baseline in probability theory. Next, the third point, the probability of an event that is certain to happen is, which is equal to 1. We refer to such events as certain events because their occurrence is guaranteed under the given conditions. Recognizing these helps us understand the bounds within which probabilities operate. Now, the fourth point. The sum of the probabilities of all the elementary events of an experiment is always equal to 1. This is a key principle because it confirms that the total probability distribution accounts for all possible outcomes in the experiment. Finally, the fifth point. The probability of an event is greater than or equal to 0 and less than or equal to 1. This sets the natural boundaries for probability values, ensuring they always stay within the range from impossible to certain events. To complete the statements with examples, for the probability of an event, it must be at least 0 and at most 1. These boundaries are essential because they make clear that probabilities are always between these two limits, inclusive. Overall, understanding these basic properties of probability helps us build a solid foundation for analyzing more complex situations in the broader theme of our presentation. Let's look at the solution here. Since the probability of an event cannot be negative, 1.5 cannot be a valid probability. Probabilities are always between 0 and 1, inclusive. So a negative number like 1.5 simply isn't possible for an event's likelihood. Now in the options given, A, B, 1.5 C, 15% D, 0.7, only the negative value is invalid. The 15% translates to 0.15, which is a valid probability, and 0.7 is also within the acceptable range. Moving on to the next part, why is tossing a coin considered a fair way of deciding who gets the ball at the start of a football game? Well, because when you toss a coin, the outcomes, heads or tails, are equally likely. This means there's no bias toward either side. The result is completely unpredictable, making it an unbiased, fair method. This ties into the broader theme of probability, understanding how outcomes work and ensuring fairness in decision-making processes. So, a coin toss is a simple yet effective example of a fair chance, which helps us see how probability underpins everyday decisions. Let's take a closer look at some advanced examples that really illustrate the key concepts we've been discussing. These examples highlight how the theories and principles can be applied in more complex, real-world situations. By exploring these, you'll see how to adapt strategies to different contexts and challenges. Remember, the core ideas remain the same, but the way you implement them can vary based on the specific circumstances. These examples serve to deepen your understanding and help you see the practical relevance of everything we've covered so far. As we go through, I encourage you to think about how these approaches might relate to your own work or projects. All right, let's walk through this slide. So the probability of not E is 0.95. That's because if the probability of event E happening is 0.05, then the probability of E not happening, that is, not E, must be the remaining part of the total, which is 1 minus 0.05. So P, not E, equals 1 minus 0.05, and that gives us 0.95. Now remember, the sum of the probabilities of all possible outcomes in a sample space must equal 1. That's why we write P, E plus P not E equals 1. Since we know P, E is 0.05, we can easily find P, not E, by subtracting that from 1, confirming it's 0.95. This example highlights a key concept in probability, the complement rule. The probability of an event plus the probability of its complement always sums to 1. This is fundamental because it helps us quickly determine the chance that an event does not happen, based on the probability that it does. In the context of our overall presentation, understanding how these probabilities relate, especially through the complement rule, lays the groundwork for more complex probability calculations. It shows how knowing one part of the probability allows us to find the other, which is a powerful tool in statistical reasoning. Let's go through the key points here. First, the probability of taking out a lemon-flavored candy is 1. Since the bag contains only lemon candies, every time Maylene reaches in, she is certain to pick a lemon. Now, because there are no orange-flavored candies in the bag, the probability of drawing an orange-flavored candy is 0. That's an important concept. If a flavor isn't present in the bag, the chance of picking it is 0. So, to answer the questions, the probability that she takes out an orange-flavored candy is 0, because there are none in the bag. And of course, the probability of taking out a lemon-flavored candy is 1, since she has no other options. This example highlights how understanding the composition of the set, in this case, the candies in the bag, directly influences the probabilities. When the content is uniform, like only lemon candies, the probabilities become straightforward. It's a good reminder that probabilities are always relative to what's actually present in the scenario. So, the required probability of 2 boys having the same birthday is 0.008. We know that the probability that they do not share a birthday, P, NSB, plus the probability that they do share a birthday, P, SB, must equal 1. Therefore, P, NSB plus P, SB equals 1, which means P, SB equals 1 minus P NSB. Since P NSB is 0.992, we subtract that from 1, giving us P SB equals 0.008. In other words, the total probability that two students share a birthday is 0.008. Now, to clarify, P SB is the probability of two students having the same birthday. Given that, in a group of 3 students, the probability that 2 students do not share a birthday is 0.992. What is the probability that they do share a birthday? This is a good example to understand how small these probabilities can be, but also how they are calculated systematically. It highlights the importance of understanding complementary probabilities, the idea that the probability of an event plus the probability of its complement equals 1. This example ties back to our overall theme of probability and how we can use logical steps to determine these small but significant chances. All right, let's walk through this example. We have a bag with 3 red balls and 5 black balls, so a total of 8 balls. The question is about finding the probability of drawing a ball of a certain color. First, for the red ball, we look at how many red balls there are, 3, and how many total balls, 8. So the probability of drawing a red ball is simply 3 divided by 8. Next, for the second part, we want the probability of drawing a ball that is not red. Since the only other color is black, and there are 5 black balls, the probability of not red is 5 divided by 8. This example highlights how we can calculate probabilities based on simple ratios of favorable outcomes to total outcomes. It also ties into our overall theme of understanding how chance works in everyday situations. Remember, these basic probability concepts are foundational for more complex problems down the line. All right, let's walk through this problem together. We have a box with a total of 5 red marbles, 8 white marbles, and 4 green marbles. So first, let's find the total number of marbles in the box by adding these up. That gives us 5 plus 8 plus 4, which equals 17 marbles in total. Now, the question asks about the probability of drawing different types of marbles at random. Remember, probability is basically the ratio of favorable outcomes to the total outcomes. For part 1, we want the probability of drawing a red marble. Since there are 5 red marbles, the probability is 5 out of 17, or 5 over 17. Next, for part 2, the probability of drawing a white marble. There are 8 white marbles, so that probability is 8 over 17. Finally, part 3 asks for the probability that the marble is not green. Since there are 4 green marbles, the number of marbles that are not green is the total minus the green ones. 17 minus 4, which gives us 13. So the probability of not drawing a green marble is 13 over 17. This example helps us see how to calculate probabilities by focusing on the favorable outcomes over the total outcomes, and how to adjust that when we're interested in not conditions. It's a straightforward approach, but really fundamental to understanding how probability works in real-world scenarios. Let's break down this problem step by step. We have a piggy bank containing different coins: 150 paisa coins, 51 coins, 22 coins, and 10 5 coins. Now, if we turn the bank upside down, each coin has an equal chance of falling out. Our goal is to find the probability of 2 specific outcomes. First, we consider the total number of coins. That means adding up all the coins: 100 of the 50 paisa coins, 50 of the 1 coins, 20 of the 2 coins, and 10 of the 5 coins. So the total number of coins is 100 plus 50 plus 20 plus 10, which equals 180 coins. Now, for the first question, what is the probability that the coin that falls out is a 50 paisa coin? Since each coin has an equal chance, the probability is simply the number of 50 paisa coins divided by the total number of coins. That's 100 divided by 180, which simplifies to 10 over 18, and further reduces to 5 over 9. Next, the second question asks for the probability that the coin is not a 5 coin. The number of coins that are not 5 is the total number minus the number of 5 coins. That's 180 minus 10, which equals 170. Therefore, the probability that the coin is not a 5 coin is 170 divided by 180, which simplifies down to 17 over 18. So, to summarize, the key points are: the total number of coins is 180, the probability of drawing a 50 paisa coin is 5 over 9, and the probability of not drawing a 5 coin is 17 over 18. These calculations highlight how understanding the total count and individual counts helps us determine probabilities in such scenarios. So here we have Gopi going to buy a fish for his aquarium. The shopkeeper then randomly takes out one fish from a tank that contains 5 male fish and 8 female fish. Now, the key question is, what is the probability that the fish Gopi gets is a male fish? To analyze this, we need to consider the total number of fish in the tank, which is 5 plus 8, giving us 13 fish in total. Since each fish has an equal chance of being selected, the probability of choosing a male fish is simply the number of male fish divided by the total number of fish. That's 5 divided by 13. This example helps us understand how to calculate probabilities in scenarios involving random selection from a finite set. It also underscores the importance of understanding the basic principles of probability, which is a recurring theme in our overall discussion on probability concepts. Let's take a moment to review the key points we've covered so far. Throughout this chapter, we've explored the concept of probability and how it applies to various situations. We've seen how probability helps us quantify uncertainty and make informed decisions. It's important to remember that understanding probability is fundamental to many fields, from statistics to risk management. As we conclude this chapter, I encourage you to think about how these concepts can be applied in real-world scenarios. Mastering probability not only enhances your analytical skills, but also prepares you to handle uncertainties more effectively. Thank you for your attention, and I look forward to seeing how you incorporate these ideas into your work. So, to wrap things up, I want to quickly touch on the overall theme of this presentation, which is about understanding probabilities and how they help us make better decisions. We've looked at various examples, and even though I've omitted some to save time, the key takeaway is that mastering these concepts allows us to assess risks more accurately and confidently. Remember, probability isn't just about numbers. It's about gaining insights into the likelihood of events happening, which can be incredibly powerful in both everyday life and professional settings. So, I encourage you to keep practicing these ideas, and you'll find they become second nature. Thanks for your attention throughout this session.